So now we're going to start talking about the atom, but before we can talk about the atom, we don't make justice to it by just saying the atom is made of particles. Let's go through the history a little bit to make sure we understand how all these findings were found, how scientists used what they knew at their time to be able to get the information that we have today. And some of the things that they did are still valid, still good. There's one place where one of the postulates is no longer valid because of what we know about the atom today, but we'll mention that when we get there. So we are going to start going back in time to the time of the Greeks. And there was this Greek called Democritus. He said, if I take a piece of anything and start cutting it, there's going to be a time where I cannot stop cutting that anymore. So matter can be broken down until there's a time where I cannot do it anymore. So he called that atomos, which means uncuttable. But the problem was that he couldn't prove it. So the Greeks, being Greeks, laughed at him, didn't believe him. It wasn't until a little bit later that one of his disciples, Aristotle, disagreed with him a little bit and framed it in a different way, which was flawed. But everybody believed him, so he got credit and Democritus didn't. Regardless of that, Democritus is considered the first one to talk about the atom, and he did that by saying that the atom is uncuttable. You cannot break it down into smaller pieces. And that's something that's still valid these days. So he did it by just comparing it to a piece of bread. That's all you need to know about Democritus. And that was around 400 BC. So way back then where they didn't have any way of proving that they could see an atom. So he just did it in his head and he thought, there's gotta be something, how I can explain this, and that's how he did it. Then it was until a little bit later when we came out with this law of conservation of mass, constant composition, and multiple proportions. The only one that I'm going to mention is the conservation of mass at this point, because matter is neither created or destroyed. And what that means is whatever you start with, you have to end up with. So if I start with hydrogen and oxygen and make water at the end, that water needs to have the same amount of hydrogen and oxygen that I started with. You cannot have more oxygen, you cannot have more hydrogen. The proportions of what I started with have to remain the same. And I'm bringing this up in here because the next scientist we're going to take a look at, which is Dalton, has some postulates in there that are based on the law of conservation of mass. So Dalton was an English guy. And this was way, way, way later on, much later than the Greeks. And he came out with this atomic theory. The atomic theory has a couple postulates. The first one deals with the same thing that Democritus said, and is that matter is made of these tiny particles called atoms. And then because everything has atoms of the same type are always the same, and atoms of different things are different. So if I have an atom of hydrogen, an atom of hydrogen will be different than an atom of boron or an atom of carbon. So atoms are different from each other. But if I have atoms of the same thing, they're all identical. Then he said that compounds are made of different atoms in very specific proportions or ratios. So water is always 2 hydrogens to 1 oxygen, but hydrogen peroxide is 2 hydrogens to 2 oxygens. And because water and peroxide are made of the same elements, doesn't mean they're the same thing. Water you can drink, hydrogen peroxide you can drink, but you will die after. Because it's not something that you should be drinking, even though it's in toothpaste and other things, but in small proportions and they help with cleaning. But drinking pure hydrogen peroxide will kill you, especially if you drink 30% hydrogen peroxide, which you can really buy in the store. The one that they give you in the store is around 3% only. Now, there's one thing in here that is addressed at the bottom. He said that atoms cannot be broken down, but that thought falls apart because atoms are divisible via nuclear reactions. Now we know that we can break atoms apart. And by doing that, by removing particles from the atom, we can get different type of atoms, or we can make new atoms. So this idea that matter cannot be created or destroyed is no longer valid today. But by the time of Dalton, that's what it was believed. So elements are made of atoms. All atoms are identical. When you combine different atoms, you get compounds with specific ratios. And then that atoms are indivisible and matter cannot be created or destroyed, with a caveat that that's no longer valid. Now, Dalton said that the atom looked like a ball, like when you play billiard. It's very dense sphere. So it's just like a ball, and that's the atom, because he didn't know anything about particles. Okay, so we have Democritus, and now we have Dalton. Things are going to start getting more complex, as you can imagine. Because now, way after, we have this scientist called J.J. Thomson, and I'll list them in here. So we have Democritus, we have Dalton, now we have J.J. Thomson. And what he did is he took a cathode ray tube, and it looks like that. It has a cathode, it has an anode, and it has a beam that moves from the cathode to the anode, meaning from negative towards positive side. Cathode ray tubes is what they used to use to make those big TVs that used to be in your grandma's house. The big white TVs that had a big tube inside, that's a cathode ray tube. The beauty of it is that beam you can control and move it using some plates, and where that beam ends up hitting, if you have a lot of beams, you can create an image. That's how they used the TVs back then. He took a closer look at that beam, and he said, okay, this beam is made of negative particles because the beam is moving from a source that is negative towards a source that is positive, because opposites attract. Negative attracts positive. If it was negative plate, it will repel it, and so it will move in the opposite direction. So because that ray is moving towards the positive plate, he said, okay, the atom has to be made of these particles that are negative. I'm going to call them electrons. So he discovered the electron and said that it was a negative particle. So now we have a first scientist that discovered the first particle the atom is made of. So Thomson is the electron. Dalton is the atomic theory. And the material is just indivisible. We know the atom is made of more particles than just the electron, so there's gotta be someone that did more than just did. Now, before we do that, JJ said that the atom, okay, he took Dalton's atom and said, okay, that is all good, but it's not just a sphere that's dense and solid. We have that sphere, we're gonna say that that sphere is positive, and then we have these negative particles that are negative, and they're embedded in that sphere. He called that a plum pudding model because in English, they had this plum pudding thing that they eat over there. It's a piece of bread with raisins inside. I think it's disgusting, but you have to tell me if you ever try it. But it's a piece of bread, and when you cut it in half, you can see all these raisins inside. So those raisins will be the electron, and then the rest of the bread is just a positive charge thing. Substance matter, if you want to call it that way. But we can see that the atom is evolving into a new structure, a new way of seeing it. So after JJ, we have this experiment called the gold foil experiment, and that is Rutherford. If you ask me of any of the scientists that you're learning about today, Rutherford is the most important. He was the best description of the atom. We are still using what he discovered to this day because it's still valid. What he did is he took a piece of gold foil, he made it into a thin piece of paper. Then he took a source of alpha particles that he turned on, and then it started beaming particles towards the gold foil. And he saw a few things happening. He was expecting for all those beam particles to go through the piece of paper and across, but that's not what he saw. He saw sometimes those particles will bounce back or got deflected, and sometimes they go through. So we'll go over what all that means in a second. But Rutherford with the gold foil discovered one more particle. I'll tell you what that is in a minute. So if we take a closer look at the gold foil. Gold foil is made of gold particles, gold atoms. All those gold atoms are aligned. And what he said was, it was like firing a cannonball at a piece of tissue paper and having it bounce and hit you. So you're throwing let's say a ball at the wall, and you're expecting that ball to go through the wall, but it's bouncing back. So three things in here. Sometimes he saw the particles going through, and others he saw the particles bouncing back, and there were other times where they were getting deflected. So three things. You need to know what each one of those mean. So if I draw an atom of gold in here, let's say that's my gold foil. If it goes through, it means there's nothing there. If it is nothing there, he said that the atom is made of mostly empty space. Made of empty space because I'm not hitting anything. Nothing is happening, it's just going through. It makes sense. Then there were cases where those particles were bouncing back. If I'm hitting something and it's bouncing back, it means it has mass. It has something in there. There's something there. So it's bouncing back. So he ended up saying that the atom has a dense center because I'm hitting something and it's bouncing back. It's not letting me go through. And then there were times where it was getting deflected. Okay. The alpha particle that Rutherford used in his experiment was an alpha particle that's positive in nature. So if the particle is positive and I'm getting deflected, what does that tell you about the charge of that center? It has to be what? Positive or negative? Positive, because positive will repel each other. Positive, negative will get attracted. So that center is positive. So there has to be something in that center of that atom that's positive in nature. He ended up calling that the proton. So JJ discovered the electron, Rutherford discovered the proton. And then he summarized all his findings saying that the atom is almost empty space with a nucleus that contains all the positive charge and mass, and is very dense. That is very, very important because we're still using that these days.
My apologies, do I understand you mean?
Yes.
I don't think we have any of the gray ones like this available, but I can see what I can find for you.
Sure thing.
How many?
Well, we have 48 students, and there's only 44.
Whoever needs a table, raise your hand, please. I just need.
They're the ones in the back.
So, do I see three back there without a table? It's hard to know.
Yeah.
Okay.
I don't need it today. So
Moving forward.
Okay.
Thank you so much.
Thank you so much. Okay. Again, he said that the nucleus contains all the positive charges and mass, and it's very dense, but the rest of the atom is almost empty space. So if you draw the atom now, That nucleus is very small. In the center of that atom, it has to be very small because most of the particles are going through the atom. Now I have in here that is surrounded by electrons because we still have to account for what JJ discovered. So there's positive particles, there are negative particles. There's one more particle, and that's the neutrons. We don't go over the experiment of how the nucleus was discovered, but it was an oil drop experiment. I'm not going to quiz you on it, so I never go over it because the protons and the electrons are the most important ones. So we have 4 scientists. You have to know all 4 scientists. You have to know what each one did, paying a lot of attention to Rutherford and the gold foil, because you will have questions on that. So now we know that the atom is made of these particles that are protons, electrons, and then this one that is neutrons. The protons are positive, as the gold foil experiment discovered. So we say that it has a charge of +1. And the mass we are going to define it as a 1 AMU. AMUs are atomic mass units, because any number that we do in class requires units. That mass is going to change, and it's going to change in a couple of weeks, not today. We're going to keep calling them AMUs for now. And the protons are located in the nucleus. Also in the nucleus is this other particle called the neutron. It's about the same size as a proton, but it doesn't have a charge. And it's there for stability of the atom, to stabilize the mass of the atom. And then we have the electrons, which are negative. Electrons pretty much have no mass. We say that the mass is 0 because it's so small. By all means, it's about 0, and it's located outside that nucleus. Now, I added in here in this table that protons deal with the identity of the atom, and we'll talk about that a little bit more in a little bit. Neutrons, they help with other properties of the atoms, which we'll go over soon as well. And then the electrons are pretty much the ones that determine the properties of the atom. It determines how things are going to behave. If you did most of you did your module for this week, so it addresses all these particles and how to calculate them and all that. We'll go over all that together to make sure you understand how to do it. So we'll start by talking about this thing called the atomic number. The atomic number is the single number in each of those boxes in the periodic table. It's in different places depending on the periodic table that you use, but it's a single number. And you'll notice that it increases from left to right and going down the periodic table. The atomic number tells you how many protons you have in the atom. It's the only one of the properties of the atom you cannot change. Meaning, if I change the number of protons, I change the atomic number. I change the atomic number, I change the element I'm dealing with. So, because it deals with identity, it cannot be changed. So, for any type of calculations you do, you leave the atomic number and the number of protons alone. Don't do anything with that. We do everything in terms of electrons. Okay, so we have neutrons that help with the stability of the atom. But sometimes those neutrons can change but because the number of protons remains the same, we say that, okay, these are atoms of the same element with different number of neutrons. We are going to call those isotopes. They're just different variation of the same element. So we have this property called mass number. Mass number is how many protons and neutrons you have in the atom. The mass number is not the same as the atomic mass. We'll talk about the atomic mass towards the end because it's a different way of calculating that. Again, isotopes are elements of the same atoms of the same element with different number of neutrons, but the number of protons remain the same. There's a reason why we have different isotopes. Well, isotopes are because when you go in nature, you can find these different variations. And we'll see when we get to atomic mass that they influence the mass that you see in the periodic table reported there. So just because you can find it in nature doesn't mean that you will have all of them in nature all the time. But we'll talk more about it and make that definition more complete in a little bit. So we have atoms. Now we have isotopes. And then we have ions. Ions are atoms with a charge. We call them cations because they have a positive charge when they lose electrons, like K plus or Ba2 plus. We'll do some examples in a little bit. And then we have anions because they gain electrons, like Cl minus. So when we talk about charge, we do it in terms of electrons. You gain or lose electrons. We never say you have more protons or you have less protons because that implies changing the identity of that atom. So we always do it in terms of electrons. And I think, let me see what's coming next. Yeah, let's do some examples now, just because it makes more sense. So let's say I have carbon. Carbon is element number 6. So atomic number 6. We always write it at the bottom of the symbol. So that's the atomic number. We need the the mass number. The mass number is the rounded atomic mass. So for carbon, the atomic mass is 12.011. So rounding that is 12. Which is the rounded atomic mass. This is what is called an isotopic symbol because it shows you the symbol of the element, the mass number, and the atomic number. From that information, we can calculate how many particles it has. So protons will be equal to the atomic number. So in this case will be 6. Electrons is going to be equal to the protons, which is also 6. And electrons equals protons in a neutral atom. Meaning it doesn't have a charge. And I'll show you how that is done in a little bit. And then the neutrons is 12 minus 6, which is also 6. Is the mass number minus atomic number. So mass number minus protons. For carbon, it's easy because all the numbers end up being 6. But let's do something different. Let's do calcium. Just because calcium is element number 20 with a mass of 40. And this one is going to do the same thing. So protons is going to be 20, electrons is going to be 20, and then neutrons is 40 minus 20, which is also 20. And you can do that for any of the atoms in the periodic table. You need to be able to calculate protons, electrons, and neutrons. You will be asked to do that in the test. So that's the case when the atom is neutral. Let's do the isotope. I'm going to use carbon just to show this. I have 3 different isotopes of carbon. I know they're isotopes because they're all carbon, because the atomic number is 6, but the mass number is 12, 13, and 14. Atoms of the same element with different number of neutrons is what we call an isotope. And you know it has different neutrons because the mass number changes. So protons is still 6 for each one. Electrons is still going to be 6 because it doesn't have a charge. Then neutrons is 12 minus 6, 6, 13 minus 6, 7, 14 minus 6, 8. The number of neutrons is changing, but the atomic number remains the same. Those protons remain the same. And that's what an isotope is. Then we have the charge, and this. Let's do Na plus, let's do Cl minus. Na is element number 11 with a mass of 23. Because the atom has a positive charge, if it was neutral, it will have 11 electrons. But because it's positive, it means it has 1 electron less. So instead of having 11, you take 1. So it is 10 electrons. The difference between protons and electrons gives you the charge. So 11 minus 10 is plus 1, which is what we have in here. The number of neutrons is still 23 minus 11, which is 12. Then we have chlorine. Chlorine is 17 and 35. So protons is 17. Electrons, if it was neutral, it will be 17. But because I have one more negative, I just add one more. And then neutrons is 35 minus 17. Which is what? 15? 18? I cannot today for any reason. Okay. Just be careful. If it is positive, you have less electrons than protons. When it's negative, you have more electrons than protons. Understanding charges, it's going to help you next week when we do compounds and naming, because you need to be able to do to determine that. Now, again, please bring your periodic table next class so it makes things easier for you to understand. So, from the experiments, we found the particles. Having the particles, we now know we have three different types of atoms. We have the neutral ones, we have the isotopes, and we have the ions, which are the ones with a charge. You need to be able to determine particles for each one of those cases. Now, that leaves us with a problem. Because I have this thing called mass number, and I have isotopes, which are different atoms of the same element with different masses. How do I report the mass of an atom in the periodic table? Because mass numbers are rounded numbers, they are whole numbers, and the reason they are whole numbers is because I cannot have partial particles. It has to be a whole particle, or I don't have it. But the atomic masses are numbers with decimals, which implies a fraction. How do I reconcile the two of them? Well, I had three isotopes of carbon, but I only have one mass in the periodic table. Which ones of those three contribute to that mass in the periodic table? Any ideas? All of them contribute, but they contribute in a very specific way. So in math, if you have several things, you calculate the average and you call it a day. In chemistry, we don't just do that. We do this fancy thing of doing things. It's called a weighted average atomic mass, which takes into consideration the masses of all the isotopes of that element and the percent abundance or fraction abundance of that element. When you go to nature and you look for carbon, let's say in this case, silicon, you see that silicon is made of, okay, this diagram is not the best one. Let's stick with carbon. When you go to nature and you look for carbon, you'll see that carbon 12, which is a first isotope, is more abundant because you can find it more often in nature than you can find carbon 13 or carbon 14. So the isotope that contributes the most, or is found in nature the most, is the one that contributes the most to the atomic mass. That's why the mass in the periodic table is closer to the mass of carbon 12 than it is to the 13 or the 14. And that's true for every element. So the way we do the calculation is we take the isotope mass, which is something that's been calculated and will be provided to you, times the fraction of abundance. So if I give you percent, you convert that percent to decimal. So the mass times the percent abundance in decimal form for each of the isotopes, add them all together. That's why it's a summation. Will give you a weighted average mass, which is the atomic mass of the element, and that's what is being reported in the periodic table. So all the elements in that periodic table have isotopes. Some of those elements have more isotopes than others, but they all have isotopes. I think there's one or two exceptions where the number is just in parentheses and it doesn't have a decimal. That means because from what is known, from what is being found in nature, that's the only one isotope that we can know of, and that's why it's only one mass. But for the most part, all elements are made of different isotopes, and you have to calculate the percent abundance based on, you need to calculate the weighted atomic mass from all those isotopes. This is something that you cannot do without being provided with the mass of the isotopes and the percent abundance. So that's something that's given to you. And it's just a matter of multiplying and adding all those answers together. The Pogil that you does a good job on doing this, and because you completed that Pogil, it means you know how to do this, so I'm just going to skip. I'll probably bring an example next class just to make sure, and we'll do some other problems to make sure that we can do this before we get into naming things. So today I'm just going to concentrate on the theory of it. So our atom today has a proton that gives us the identity, has a neutron that helps us with understanding what an isotope is, because it defines the mass of that atom. And then we have the electrons because they define the charge of that atom. And there's one more thing I had to show you how to do to make sure we understand how to do this. So we have isotopes, and I told you this is the isotopic symbol because it has the mass and the atomic number. There's another way you can write that. You can say C-12, that's a dash, that's not a charge. That's carbon 12. It's another way of writing the same information. It doesn't have the atomic number because by knowing the symbol, it implies the atomic number. Once you know the symbol, you know what atomic number it is. So it is 6 for carbon. That doesn't change. So you can write it into these two different ways. Is something I want to make sure you understand. You would assume the atom is neutral unless you have information that tells you otherwise. You either have a charge, you have a plus or a minus in it, which will tell you that electrons are going to change, or you are given the mass number, which tells you that the mass might be different. I mean, the number of neutrons might be different than what you normally have. So you just have to be careful when you're doing these problems. Whatever, if I were you, whatever, I get something like this and I have to calculate particles, I'll try to do as much as I can with the information given. If and only if I cannot complete doing the calculations with the information given, then you can look at the periodic table. I just don't want you to start grabbing masses from the periodic table and then getting the number of particles incorrect. You just have to be a little bit careful. Okay, let's see. And that's it on atomic theory.